Hello, how are you today? I hope you're having a good day so far. We're going to start today the structures topics. It's one of the most, not the most, but one of the very important topics in our syllabus, and it's very easy and it's very interesting. And a lot of questions in paper 2 and paper 4 require deep understanding of this topic. Structures is different than talking about atomic structure. In the previous topic where we talked about the atomic structure, we were talking about the atom, how it behaves, how it reacts, what are the particles it's made of, and so on. Structure is a bit different because here I'm looking at after the atoms have bonded and produced a compound, do they have a specific arrangement or they are just simple structures? And this is what we will be looking at in today's lesson. Before we start the structures section, I'd like to explain something that is very important. The difference between a bond and a force. So in the previous topics where we studied bonding, we have the molecule of water. This is one molecule of water. Of course, if I look at water, it's made of oxygen and hydrogen. They are two nonmetals, which makes it a covalent compound. So here, this over here is a covalent bond. Covalent bonds are extremely strong bonds. They are not weak bonds because sometimes there's a misunderstanding with students when they study the difference between ionic and covalent compounds. We always say that ionic have a high melting point and covalent have a low melting point. So students assume that covalent bonds are weak, and that's not true. Covalent bonds are extremely strong bonds. Then why do they have a low melting point? Here's why. This is a water molecule right here, and this is another water molecule, and another water molecule, and so on. I can go on and on. These are all water molecules in a liquid state. If I want to boil the water, it means I want to change it into a gas. And we all know that changing from liquid to gas is a physical change, not a chemical change. So the water molecules here on the left-hand side, they are in a liquid state, and here they are in a gaseous state. If I look at the liquid state, the water is O bonded to two H's, and the covalent bond is still there. If I look at it here, it is still bonded oxygen and hydrogen, and nothing has changed. The only difference is that the molecules became far apart. So what actually happened here is there's a force holding the molecules together. These forces are what keeps the water in a liquid state. زي الكلبشات. ده كلبش ماسك الwater molecules ببعضها. I had to say it in Arabic so you can imagine it with me. أنا ماسكة المولكيول دي بالمولكيول دي بكلبش. لو أنا عايزة المولكيولز دي تبعد عن بعض, then I have to break this down. And this is what happens here. So the red dots here are intermolecular forces. They are forces between the molecules. And this is what we break when you boil the water. And that's why it's a physical change, not a chemical change, because the water did not change chemically. It is still made of two hydrogens bonded to one oxygen in a covalent bond, and I did not break the covalent bond. So covalent compounds have a low melting point because the forces between the molecules in covalent compounds are weak. الكلبشات ضعيفة. So the molecules separate from each other at a low temperature. So whenever we're talking about melting and boiling point, you automatically think of forces. So if I say, for example, water has a boiling point 100 degrees, and ethanol, which is another covalent compound, has a boiling point of 78. By looking at these boiling points, I automatically can say that the ethanol has weaker forces than the water. We do not refer to the bonds because both compounds are covalent and covalent bonds are very strong. Then why the ethanol has a lower boiling point? Because it has weaker forces between the molecules. So you always refer to the forces when you're talking about melting and boiling point. Okay. The first structure we're going to look at today is the giant ionic lattice. Of course, needless to say, if it's called giant ionic lattice, then it's for ionic compounds. So without even thinking, all ionic compounds have giant structures. I want to go back here for a minute and let's look at this summary together. And if you can write it down with me, please do. Structures in general, before we start looking at each structure, there are four structures, four kinds of structures. Giant ionic, giant metallic, G for giant, and giant covalent, and I'm going to put this alone, simple molecular. So basically, when you study this part, just learn the general map, which is the one right here in front of you. There are four structures: giant ionic, giant metallic, giant covalent, simple molecular. The giant ionic, of course, it goes without saying, it belongs to, it belongs to the ionic compounds. Oh, I'm sorry about that. It belongs to the ionic compounds. As for the metallic, it belongs to metals, so sodium, magnesium, potassium, copper, whatever the metal is. All metals have a giant metallic structure. Giant covalent, there are only three examples that you need to learn: diamond, graphite, and silica. If you are in grade 9, ignore the silica. And simple molecular, that's basically all the other covalent compounds. So not all covalent compounds are giant. You have three examples that you need to learn, or if you're in grade 9, 2 examples only. And the rest of the covalent compounds are simple molecular. So the word molecular here means covalent. When I say the word giant, you imagine something big, and that's actually true. A giant structure is a structure made of infinite number of atoms or molecules. So giant structures are made of a huge number of atoms, all connected together, making a specific structure. Simple is simple. The name describes it, such as carbon dioxide. Carbon dioxide is a gas. Each molecule is moving randomly in all directions. The carbon dioxide molecules do not come together and bond or make a force with each other and make a specific structure with specific properties. This does not happen. So simple structures are smaller structures. And you can imagine, common sense, a giant structure made of infinite number of atoms will have a high melting point, while simple structures have a low melting point. So that's the first difference that you need to know. So if I told you structure X has a very high melting point, you automatically think giant. Has a low melting or boiling point, you automatically think simple. So that's the first thing you do to differentiate between the high melting point, the giants and the simple. If they have a high melting point, we just said 5 minutes ago, then they must have strong forces. And this is what we will look at in the coming slides. What kind of forces are here? What kind of forces are here? And what kind of forces are here? Why do they have a high melting point? Simple molecular structures, they have a low melting point. So if I ask you why, you can automatically say they have weak forces between their molecules, and these weak forces do not need a huge amount of energy to overcome. So now let's look at these three structures here and know and learn why they have a high melting point, or what kind of forces makes them have a high melting point. So the first structure is the giant ionic structure. And of course, it belongs to the ionic compounds. We call it a lattice because the word lattice means a specific arrangement. So ionic compounds are made of positive ions and negative ions. For example, sodium chloride. Let's look at this structure. Sodium is in group 1. Let me remind you real quick. And chlorine is in group 7. So what happens is the sodium loses 1 electron. The sodium becomes a positive ion and the chlorine becomes a negative ion. These ions, because they are oppositely charged, they attract each other and they make the compound sodium chloride. Is it that simple? No. يعني sodium chloride does not exist كده as one sodium ion and one chloride ion bonded together and that's it. No. It makes this structure right here. So millions of sodium ions and chloride ions come together and make a cube form, which is called the lattice. So that's why we call it a giant ionic lattice, because it's not just simply one sodium and one chlorine. It is millions of sodium ions and chloride ions all clustered together in a specific arrangement. If I look at this structure where we have positive, negative, positive, negative, positive, negative, and so on, all of these are oppositely charged ions. So you can imagine in في very strong forces attracting them. So there is very strong electrostatic attraction holding this structure together. Of course, strong electrostatic attraction makes it a hard structure, makes it have a high melting point, because it's a giant structure of oppositely charged ions, opposite, واحدة positive, واحدة negative, واحدة positive, واحدة negative, and so on, held together by strong electrostatic attraction. Strong electrostatic attraction, يبقى a lot of energy to break it, يبقى high melting point. So why do they have a high melting point? Due to the strong electrostatic attraction between the positive and negative ions. So that's number 1. Number 2, why are they a good conductor of electricity when molten or aqueous only? Electricity is free electrons, basically. عشان أقول إن في كهرباء ماشية في السلك، مين اللي ماشي في السلك؟ Free electrons. Electrons that are moving at a very high speed. In order for these electrons to move at a very high speed, they need to be in a medium that allows the movement. And let me give you a very simple example to make you imagine what I want to say. If I'm in a classroom and I'm working and my students are sitting in front of me and it's a working day, I cannot just start running. لأنه المكان اللي أنا فيه ما بيسمحش بده. أنا محتاجة ميديم يسمح إن أنا أجري. فلو رحت النادي ممكن أجري. ليه؟ لأن الميديم والألاود، المكان والألاود. The same thing with electricity. If I look at this structure, all the ions are clustered together and vibrating in their position, بس ما فيش أي حاجة بتتحرك. Everything is so stationary. والكهرباء عبارة عن electrons بتجري. فالelectrons لما تيجي تعدي من هنا مش هتقدر. The medium doesn't allow it. ده كده يعني as basic as I can. يبقى لو الميديم doesn't allow the movement of free electrons, it will not conduct electricity. فالionic compounds, when they are in a solid state like this, the ions are not moving around, they will not conduct electricity. What happens when I melt the ionic compound or when I dissolve it in water? الlattice D breaks down. So now the positive and the negative ions are moving around, freely moving. So they can allow electricity to pass through them. هل ده معناها إنه any liquid can conduct electricity؟ لا طبعاً. لازم يبقى liquid وفيه charge. That's why a covalent compound in a liquid state will not conduct electricity. لأن covalent compound ما فيهوش ions. لازم يبقى عندي حاجة charged. So ionic compounds are good conductors, yes, بس under certain conditions. اللي هي إيه certain conditions دي؟ Molten or aqueous. And why is that? The ions are free to move and they can carry the current. So that's the giant ionic lattice. I think it's very easy. All you need to know, it's made of alternating positive and negative ions. It's a giant structure, strong electrostatic forces. That's why it has a high melting point and it conducts electricity when molten or aqueous. Another thing that I want you to notice, one last thing, the negative ions are bigger than the positive ions. So when we represent an ionic compound, we have to draw the ionic, the negative ion bigger than the positive ion. So that's the giant ionic structure. We'll move on to the next giant structure, which is the giant metallic. Before we move on to the giant metallic, I would strongly advise you to hit the pause button and study the giant ionic. Just let it sink in before you move on to the giant metallic. Giant metallic, of course, from the name, metals. So in the exam, he will ask you to describe the structure of sodium or describe the structure of magnesium or describe the structure of copper. They are all metals. They are all giant structures. Metals look like this. Let's look at the structure together. Don't read the description, just look at the structure. This is, for example, magnesium. Or you know what? Let me draw it and explain it first, and then I show you the original drawing. Let's look at a metal such as magnesium. Magnesium has 2 electrons in the outer shell. So let's imagine in this is a strip of magnesium. جبت a strip of magnesium وبتفرج عليها بمكبر. I'm going to see the magnesium atoms. Of course, it's a solid, so the magnesium atoms are regularly arranged in layers. I will also see something like this, something running in the structure, like this. It looks like a cloud moving in the form of a wave. What's this بقى? Let's see. This is a magnesium atom. I'm going to take this وأكبرها لكم هنا. Magnesium atom is made of a nucleus surrounded by 2, 8, 2 electrons. These 2 electrons in the outer shell supposedly should be rotating around the nucleus. In metals, they don't do that. They leave the outer shell and run within the structure, between the layers. This magnesium atom is going to do the same. The 2 electrons in the outer shell will leave the magnesium and start running in between the layers. So these electrons here are freely moving. They're not bound to the atom. بيسيبوا الأتم ويجروا في الستراكشر. I always explain it in my class زي الناس اللي رايحة تصلي الجمعة. تخيلوا كده معايا إن كل أب أخد معاه ابنه ماسكه في إيده ونزل يصلي، ووقفوا يعني صفوف كده عشان يصلوا، وأول ما الصلاة ابتدت كل عيل ساب باباه وطلع يجري between the layers. وأول ما الصلاة بتخلص كل واحد بيرجع لباباه تاني. يعني لما المغنيسيوم يجي رياكت، التو الكترونز بتوعه راحوا فين؟ راحوش حتة، هيرجعوا له تاني and the magnesium will react عادي ويعمل ionic bond وكل حاجة تمام. بس طول ما المغنيسيوم كده ستريب في حالها محطوطة في اللاب، how does it look like? This is how it looks like. Layers surrounded by free electrons. These are called free electrons. ليه free? They are not rotating around the atom. They are moving freely within the structure. The magnesium atom here, for the moment, becomes a positive ion. ليه؟ لأن التو electrons بتوعها مش موجودين. راحوا فين؟ بيجروا في الستراكشر. So right now, if I want to describe the structure of metals, it looks like this. It is layers of, look at the highlighter here with me, layers of positively charged ions. Why are they positive? Because the outer electrons are not rotating around the atom. To form sea of delocalized electrons. اسمهم delocalized عشان هما مش في مكانهم. Or we can call them free. So now I have positive and negative. Positive and negative يعني في strong attraction. Strong attraction يعني high melting point. So why do metals have a high melting point? Due to the strong electrostatic attraction between مين ومين بقى هنا؟ The positive ions and the free electrons. In the ionic structure, it was strong attraction between positive and negative ions. Here, it is strong attraction between positive ions برضو بس negative free electrons. مادام الستراكشر فيها free electrons يبقى electrons بتجري، يبقى this is a medium that allows the passage of electricity. That's why metals are good conductors of electricity. يبقى they have a high melting point. Why is that? Due to the strong attraction between the positive ions and the delocalized electrons. Good conductor due to the presence of sea of delocalized electrons between the layers. So ionic compounds have free ions, metals have free electrons. Don't confuse both. The last thing, malleable and ductile. Malleable and ductile يعني you can hammer them or stretch them and they do not break. Again, let's go back to example الناس اللي بتصلي يوم الجمعة. And bear with me, هو example عبيط شوية بس إيه؟ Try to imagine it. تخيلوا كده إن الناس واقفة صفوف وكلهم لازقين في بعض بالظبط. وجا عيل رخم زق واحد من وراه. اللي هيحصل إيه؟ كلهم هيقعوا. لأن اللي اتزق هيزق اللي قدامه هيزق اللي قدامه and the whole structure لو أنا واقفة بصور من فوق هلاقي إن منظر الصفوف اتكسر. This is what happens with non-metals. الميتالز بقى look at the structure here. العيال اللي بتجري بقى بتجري بين الصفوف هتخلي الرجالة تلزق في بعض ولا هتخلي في مسافة؟ هتخلي في مسافة. زي هنا the electrons are running between the layers so they do not allow the layers to be packed over each other. So now when you hammer the metal هياخد ويدي معاك شوية. There is space for the particles to slide before it breaks. أي حاجة في الدنيا أنا ممكن أكسرها، بس metals they can withstand some pressure and bend before they break. Okay? So that's what we mean by the presence of delocalized electrons between the layers allow them to slide over each other. So the presence of free electrons in the metals is the reason for the three properties. This is a property, high melting point. Why? Due to the attraction. دايما melting والboiling point related to a force of attraction. So high melting point يبقى a strong force of attraction between هنا the positive ions and the free electrons. Good conductor of electricity عشان free electrons between the layers. Malleable free electrons between the layers برضو، بس هكمل الجملة allow them to slide over each other. The attraction between the positive ions and the negative electrons is called metallic bonding. And I don't want you to think in this is a bond. البونز نوعين ionic و covalent. الميتاليك bonding هي strong attraction between positive و negative electrons. We call it metallic bonding عشان أفرق بينها وبين الاتراكشن اللي في ionic compounds والاتراكشن اللي في الميتاليك structure. So that's the giant metallic structure. Let's move on to the giant covalent. The giant covalent, you basically have diamond and graphite. That's for grade 9. Diamond and graphite. If you're grade 10, you will add to it silica. I'm adding the fullerene because it comes a lot in the exams. I'm just going to talk about it, but later on. So now let's talk about diamond and graphite. When you're done with diamond and graphite, if you're in grade 9, you can switch off the video. You don't need the rest. Diamond and graphite. Diamond and graphite, they are both elements. They are not compounds. They are made of the element carbon. Carbon is a miraculous element because it can exist in so many forms and it can make so many compounds. Today we are studying the diamond and graphite. Diamond and graphite are both made of the same element, which is carbon, but they have totally different properties. The diamond and graphite, I like to explain it أكني جبت Lego blocks. And again, I need you to imagine it with me. If I got Lego blocks, the same size, the same color, the same material, everything. وجبت Lego blocks الأولانيين and I attached them to each other in a very compact form. Millions of blocks all connected together like this. والblocks التانية اللي هو the same size, the same color, everything is the same. I connected them to each other like this. I made layers and I connected these layers. خليتهم يقفوا فوق بعض كده بأقلام. I got a couple of pens and I sort of balanced the layers over each other. If I ask you now, which structure would break down easily? I'm sure you all will say graphite. اللي هو this one, the layers. Why? Because the pens holding the layers are not very strong. So the layers will slide over each other very easily. These pens here are what we call them forces. These forces holding the layers are not very strong. أكني بنيت عمارة وعملت كل دور معمول من طوب أحمر وأسمنت وقوي جدا، بس العواميد اللي ماسكة الأدوار في بعضها ضعيفة. So now it's easy to fall apart. So this structure right here is easy to fall apart. But this one is stronger, or harder, although they are made of the same kind of Lego blocks. The same with diamond and graphite. They are both made of the element carbon, but if I go back to this slide here, if I look at the graphite, This is one layer of graphite, and this is another layer of graphite, and this is another layer of carbons. And all of the layers are attached to each other with weak forces. So this makes the graphite a soft structure. We added to the lead pencils عشان أخلي القلم ناعم على الورقة. كل ما القلم يبقى فيه جرافايت أكتر، كل ما القلم يبقى ناعم على الورقة. Pencils are made of lead. Lead is a metal, and it's a very hard metal. So we add a little bit of graphite, so we make the pencil softer on the paper. Why? Because graphite is made of parallel layers, and these layers are held together by weak forces. If I look at the diamond here, diamond is more of a compact structure. It is made of carbon, and they are all covalently bonded, such as the graphite. In the graphite as well, all the carbons are connected to each other by strong covalent bonds, and the layers are very strong, but the forces holding the layers are weak. So here, every carbon is bonded to 4 other carbons. Carbon bonded to 4, and so on. Every carbon is bonded to 4, and this structure here, we call it a tetrahedral structure. Tetrahedral, it's a very strong structure. So the diamond is hard. Why is that? Because it's a giant structure. Every carbon is bonded to 4 in a tetrahedral arrangement. Diamond is a bad conductor of electricity. When I tell you bad conductor, المفروض لو انتوا فهمتوا التوبيك من أوله على طول تقولوا يبقى no free electrons and no free ions. يبقى الستراكشر دي ما فيهاش أي حاجة freely moving. And this is true. Every carbon is in group 4. It makes 4 covalent bonds. And here, فعلا, every carbon is bonded to 4. So all of the outer electrons are occupied in the bond. They cannot be free. So diamond is a bad conductor of electricity. So here, read with me the description. Each carbon bonds with 4 carbons. All the covalent bonds are identical and strong. No weak forces. It does not conduct electricity. It has a very high melting point. Has a very high melting point. هنا بقى, I'll tell you why. هنا ما فيش forces. So in order to melt the carbon, يعني I want to separate, the diamond, I want to separate the carbon atoms من بعضها. To separate the carbon atoms, يعني I need to break the bond. Covalent bonds are extremely strong. So to break a covalent bond, a huge amount of energy has to be supplied, and that's why diamond and graphite have a very high melting point. Because in giant covalent structures, we do not break forces. The covalent bonds, and the examiner is going to look for this. Strong covalent bonds are broken, which require a huge amount of energy. And that's why we use diamond in cutting and drilling and so on. In graphite, there you go. These are the layers. The layer is very strong. The layer itself, extremely strong. But the forces holding the layers are weak. So graphite is soft. Graphite is a good conductor of electricity. Why? In graphite, carbon has 4 electrons in the outer shell. But every carbon is bonded to only 3 carbons. هو ربنا خلقه كده. This electron here that is not bonded بتسيب الكربون وتجري في الستراكشر. By now المفروض بقى تكونوا فهمتوا الثيتا في الموضوع. حاجات بتجري يبقى good conductor of electricity. ما عندكوش حاجات بتجري غير حاجتين، يا ions يا electrons. الفري ions في ionic compounds only when they are molten or aqueous. The free electrons are in metals and graphite. So why is graphite a good conductor of electricity? Because every carbon is bonded to 3 and there are free electrons between the layers. Between the layers هنا is a key word in your answer, which can carry the current. So each carbon is bonded to 3, strong covalent bonds. It has a very high melting point. It has a very high melting point because, again, to melt graphite أنا لازم أكسر اللاير. I have to separate the carbons, and they are bonded together by a strong covalent bond. So a huge amount of energy has to be supplied. It is soft. طبعا it is less dense than diamond, لأن diamond is a compact structure, but graphite is made of layers, and all of what we said. Grade 9, you can switch off the video. Grade 10, we have nothing more to say, but silica, if you look at it, very similar to diamond. Look at the diamond structure, very similar to the silica. So this is a tetrahedral structure, but it's made of silicon and oxygen. Every silicon is bonded to 4 oxygens. Silicon is in group 4, so it makes 4 bonds. 1, 2, 3, 4. Oxygen is in group 6, يعني عنده 6 electrons, يعني الvalency بتاعته 2. It shares with 2. So every oxygen is bonded to 2 silica. So look at the oxygen here, the red one, bonded to 2 silicons. And look at the silicon هنا اليellow, bonded to 4 oxygens. And you have to learn this information. إنه every silicon bonded to 4 oxygens and every oxygen bonded to 2 silica. It has the exact same properties of diamond. It is very hard. High melting point, again, because we have to break the strong covalent bonds, which require a huge amount of energy. It's a bad conductor of electricity. يبقى أكيد no free electrons or free ions. And that's it. They are both hard. They have a very high boiling point. They are insoluble in water, bad conductor. But why is the silica cheap and the diamond is expensive? Because silica is sand. Sand is highly available. Okay? So to wrap up the giant covalents, a standard answer. Why do they have a high melting point? Because strong covalent bonds are broken, which require a huge amount of energy. خلصنا. Diamond and graphite, made of carbon. Diamond tetrahedral, every carbon bonded to 4. Graphite, layers with weak forces, every carbon bonded to 3. Diamond, bad conductor, no free electrons. Graphite, good conductor, has free electrons between the layers. Silica, similar to diamond, tetrahedral, made of silicon and oxygen. Silica bonded to 4 oxygens, oxygen bonded to 2 silicons. You can repeat the last sentence I just said. Listen to it one more time. Try to write it down so it can sink in, okay? Thank you very much for listening. I hope this video is beneficial, and bye-bye.